not amplitude. So I don't need to have problems, or I don't need to worry about the sensor location or about the kind of excitation I have. If I have excitation, so I need to check that I'm able to do with different kind of engines, different kind of combustions, and we will see some results. Other thing is that the pegging effect, the effect of knowing the pressure reference is not very important because I'm doing this in the high pressure region of the signal. So even if I had 1 bar error, it would be a 1%. In 1 bar error is a lot of error in pegging. And finally, to say, inside the cycle, I'm able to provide a quality measurement of my guess, of my observation of the mass. So let's move to some results. Well, we have worked in many engines with research-grade sensors, with continental sensors for RCCI, diesel, and so on. So I will show a couple of engines just for you to appreciate that this is working. This is the first engine. This is an RCCI. We use a real-time PXI for the acquisition of the signal, and you know the spectrogram. So this is a big bore engine. This is 2 liters engine for the cylinder. For me, that's big bore. It's small. So I need to check your engines. That's another important thing. There's CSU engines are not here, and I would love to have them. So the thing is that combustion is very fast because it's RCCI, and the bigger the engine, the lower the frequency. That means that the attenuation is lower. So applying the method here is very, very easy. So some study results. This is one operation point, and I have different cycles, and for each one of the cycles, this is the measurement I'm getting, and the standard deviation I get from my signal. And I'm comparing with the test cell measurement, and you can see that the agreement is very good. Even I have some outlier, but we should check if it's a problem of the engine because it's VBT, it's completely flexible VBT, and time to time we have some strange cycle. And here we have several operation points moving from low mass to high mass, and you can see that the agreement between the actual, well, the test cell system for measuring and the new method is quite good. Let's check dynamics. Here in gas and VBT, we change from one cycle to the next the intake valve closing. And here these are 3,000 cycles. You can see that from one cycle to the other we change directly. And here are the results. Well, the results the method that is providing are the gray dots. And then with only, I think it was a 10 cycle moving average, you can see that, wow, this is, if someone is able to measure air in an internal combustion engine with this speed, I pay a dinner. Let's go to the other engine. This is a small engine, automotive engine. It's, let's say, half a liter cylinder. And this is a special engine because it has negative valve overlap. So in this engine, we run a special combustion mode, so we want to have very, very hot residuals. So we open this valve, but we close again before finishing the exhaust stroke. So we have some recompression. And the advantage of this is that the exhaust stroke is completely separated from the intake stroke. And with that, we can play something more. If we assume, here you can expect gamma and so on. If you assume that here, the gas inside the cylinder is just behaving with a polytropic, well, with that, you are able to write the residual mass as a function of pressures, temperatures, and gamma. But as I'm able to provide an estimation of the mass inside the cylinder, I can combine this with the previous method, and with that, I can go to something like this. The residual mass is the mass in the cylinder. That's something that only depends on pressures, and that's all. And that means that in an engine with MBO, I'm able to provide not only the mass inside the cylinder, but the residual mass fraction, the exhaust mass, and the intake mass, cycle by cycle. Does it work? Well, it's something we need to discuss. And also in this engine, we have other problems, is that we have many different combustion modes. So we have SI, SACI, and HCCI. I hope you are familiar with that. SI is spark ignited. SACI is spark-assisted compression ignited. So we have a spark ignition, we create a flame that compresses the rest of the mix and that ignites. So here you can see there's a flame propagation, and then you have the fast combustion of all the engine, of all the mix. And HCCI is just the self-ignition of the mix. And, well, the faster the combustion, here you have a couple of examples of two cycles, the ones that are marked. Here the spectrograms show a very definite resonance, but the slower the combustion, the resonance is mixed. And if we go to spark ignited, in some cycles we can see it, while here we lose the signal, and in others we cannot see it. So for applying the method to spark ignited engines, we need, let's say, a very soft knock, at least. We need some knocking in the signal. So let's go to results. This is in HCCI operation for residuals and nexus mass. And cycle by cycle, we are able to provide estimation. And if we compare with spark ignited, well, in spark ignited we have a problem, is that sometimes we are able to provide estimation, but only in some of the cycles. So the method works, but only we have some knock. But even in knocking cycles, I can detect that. So I think this is what's happening there. So some final results for this engine, and I move to the last part of the presentation. This is the residual mass and the intake mass estimation for the engine, comparing the measurement in the test cell with the results, the measurement with models with the results, and you can see that the agreement is very good. And once again, the dynamics of the system when you have a step in the bulk timing are very good. So, okay, moving to the conclusions, it's possible to obtain an accurate cylinder charge estimation. We can provide also quality metrics for that, and we can compact the method in a way for going time frequency analysis and going to real-time controllers. So just for finishing the presentation, let's say the technical presentation, let's thank the people paying this, because you need to pay for this, and so it was for IAB, and also the Department of State for the Fulbright grant, and the University of Michigan also collaborate a little in the funding. And Renault, Volvo, and Toyota, they did not pay, but they provide data for checking things, so I need to include them, let's say, in a fussy way here. And that takes us to the question of what do we do for funding the research? And this is one of the points that you want me to cover. So for me, it's very important to use the involvement. It's not only because they give money, it's because they provide you the latest technology. I think doing research in internal combustion engine as a university alone makes no sense. I need to be near the OEM for knowing what will be in the market in the next years, especially for engine control. I cannot work in something that is very old. And that has a cost. You need to shape the research. You need to look for something that is interesting to the industry. You cannot do whatever you want. These are my sponsors of the last 5 years, so Peugeot and Ford, Jaguar Land Rover, Volvo, and then some integrators of engines and some, let's say, engineering service companies. And for sure, you also need the public funding. And this is university or regional, this is national, and this is also transnational. In my case, it's European, and that goes to collaborative projects where you have consortiums with the industry. I think it's quite similar to things you have here. So these are my numbers for 2010 onwards. So I'm proud. You need to put the numbers in Spain. It's not the US. So we are poor guys, but I secure 1 million myself for the university, and I collaborated in more than 500,000 more in other projects with other professors. So moving to the future, what I would like to do, well, just try to replicate this in the US. So one thing is leveraging the automotive sponsors. So, well, this is the people that have found me. I usually have meetings with the industry every 2 weeks and presenting things, and they will get funds. And I feel that this would be easier from the US than from Europe, or from Spain. Europe is very big. And the other thing is looking for synergies with Colorado State industrial partners. So just looking for energy generation and how to get this advantage of having the automotive technology applied to other engines. So I'm here also to learn, and I feel there's potential for that. And for sure, public grants. We need to go to the Department of Energy, to NSF, or to different public money that is available for these kind of works. Just thinking about constructions, and also here you need to set the research, but perhaps in the other direction. So being innovative and having new solutions. So just for finishing, from research to teaching. So I'm a professor, I like teaching, and how all this goes into teaching. So that was my view of the content things, and there is a thing. If you are a mechanical engineer, you need to know also about electronics, mathematics, controls. If you need to do a presentation, you need to have IT guys for switching on the Canon, the beamer. So, multidisciplinary approach from thermodynamics to control engineering. I'm very into new technologies. I don't think we can teach just taking a book from, I don't know, from the 18th century and just teaching the fundamentals. They are there, but you need to apply in the final programs to the latest technology. So I always try to do an effort to do that. And advanced tools such as modeling and real-life data processing. I feed the students with data from experiments. So I'm a little late, so I will be fast, sorry. Competence to develop, for sure, engine knowledge, but also modeling. Physical, but also control-oriented. Let's say, not for running in 2 weeks in your computer, but for doing fast in the controller. Transient measurement, I think this is something that in CSU is missing, that is taking the dynamics of the engine. So measuring fast, cycle by cycle, and with very strict time approach. Signal processing, data fusion, applied control, and a lot of software prototyping techniques. So going to ideas to the application on the final engine. So some things I do with the students. Well, here I mark more or less what's the level for that. So 0-dimensional and 1-dimensional model. So for example, we have an open source code called Open1, that is GD Power Like. And we do simulations with engines. And we get that for optimizing the engine behavior for very simple engines or for very complex turbocharged engines where we do boosting system analysis. That analysis from real life data. So we take data from the experiments and we use with the students. So there are faults, all the problems we have in the real life. And I want the students to dig into that. Also for that, I think it's very interesting. It's an activity, it's a very cheap activity, actually. It's using OBD and GPS for getting data. So all your car has an OBD port, and you can get a connector. This is $5 in Amazon. You can get a software. This is $5 in the store, and you can just measure what's happening with your engine, with your car. And with that, you can evaluate. Well, the first thing is real-life data, measurement errors, and you need to dig a little into the data. But there are a lot of interesting things. You can just get your vehicle speed profile, see what's happening with the engine temperature, and so on. And with that, you can just put the theory into the real-life data. Let's say it's undergraduate level, so it's very easy things just for having this feeling of what's happening with a real engine in operation. And even you can do quite advanced things, like analyzing how fuel efficient you are driving, and also with these speed profiles, you can try to check if it will be better to have a small compact car, a big car, a hybrid electrical vehicle, and so on. So this is something we have done with the students. And another thing is going, sorry, go into the real engine control. So in my university, I get an agreement with Ford for accessing to Euro 5 controllers. So we have the documentation, and the students can check that, and we can dig into the software components and analyze the idle speed, GR controllers, knob limiter, and so on. And we can also play with the calibration. We can change the combustion characteristics, the boost pressure, and see what's happening with NOx and efficiency. And finally, and this is more for PhD students, we can do bypass of the engine, so we can inject new control algorithms in the ECU and just to do new ideas, to put new ideas into the market. And for finally, for finishing, student projects, they are everywhere. So I've been always very active and I'm very committed into creating positions. So that's PhD, but also master and undergraduate positions for doing that. And one thing I'm very happy is that with these competencies that is internal combustion engine and control, today you have a lot of work. And this is very good that many of my resident students, or most of them, are in the automotive industry working. And with that, sorry, I took 4 minutes more, this minutes, and I'm open to your questions.
Well, I really enjoyed your presentation, technical presentation. A couple questions. So, since you can choose multiple windows to your analysis for a given cycle, could you, in addition to measuring mass, temperature, can you also measure gamma? And one of the issues, I mean, with gamma for you, you calculate it probably.
Yes, we.
Because to me, that's always kind of a, sort of hand-waving thing.
In your case, I think it's more complicated because you are using different fuels, so the exhaust gas composition can change a lot. So I need to think about that. In our case, gamma, we did in one of the publications the numbers. So from pressure to combustion components, the variation of gamma was like 4%. So if you go to the center value, it's like a 2% error, and we just thought that was okay. So the other thing we are trying to do is, if we have sufficient excitation and we have very well calibrated the engine, we can try to get low by. So because you move the window and you see that the mass goes down.
Right.
So I'm not very enthusiastic about gamma, but if you have an exhaust sensor, perhaps you can do it.
Yeah. And one other one is a little more practical. So we do some similar work with Woodward. Real-time engine control using some of the pressure measurement, more along the lines calculating heat release rates during engine control based on heat release, CA50, controlling CA50. The question though is to do it practically using sort of onboard hardware, limitations come down to sample rate, the amount of onboard memory that you can store, and the amount of floating point operations that you can do. So it seemed to me, in order to do your Fourier transforms and stuff, it's probably a pretty high sample rate. Well, have you thought about implementing this? I mean, I agree with you 100% that this is where things are heading. But to implement it in a commercial vehicle, you're going to have to really compact your algorithm.
We did it. So well, several things. One thing is things are changing. If you just talk with Infineon people, you will be, well, in the past the ECU was like an old PC from the 80s.
Yeah.
Today it's like a mobile phone. So they are going to quad core and they have DSP. So the computing power is there. So I think that now there is like a gap for doing this kind of things because the new generation of ECU will have a huge amount of computation power. After 2 years, everything will be collapsed again because you increase, everyone wants more computation power, and you just, well, everything gets cramped and crowded in a moment. But now I think there's some opportunity. But as you said, the big thing is the frequency rate. It's not that big. If you do crank angle base, it's like 0.2 degrees per sample. depending on the engine speed. In the case of a stationary engine that is very slow, we need to go to a bigger resolution. But in our result, what we found is that doing the crank angle based acquisition is not the best thing, because you have variation inside the instantaneous speed of the engine, so that means that the you are seeing a frequency that is not the real frequency. So we go to time-based acquisition, that's much cheaper. So going, well, you could have whatever you want. We are trying to convince manufacturers, and we are in contact with some of them. I'm not sure if this will arrive. My feeling is that putting this into the cars makes no sense for today, but doing this for research is very cheap and convenient. So now I'm chasing Kisler people for just putting in kilos that I think is the market for this.
Yeah, I would echo Tim's comment. Very enjoyable presentation. I have one observation to make in your modeling, that when you relate the wave speed of the disturbances, that equation is for infinitesimal pressure waves. And so that would then introduce more uncertainty in your modeling. So perhaps if you use more of a wave speed model that accounts for finite size pressure differences, it may tighten up some of the results.
We try to do that, but what we finished doing, well, I'm at the end just thinking in application.
Sure.
So what we found is that the problems were, well, for doing that you need to consider all the different modes and just go into the real simulation. So you will lose let's say, the real-time application of the system. And the other thing is that when you go to this part following the combustion, that would be, let's say, the more critical, there, well, you cannot just think that this is a resonant chamber. There you need to know where is the pressure wave exactly on the modes, and also the temperature is not, let's say, homogeneous. And my impression is that it makes sense as a very nice research, but will be not useful for the final application. And I'm always very oriented to that part. So I will be very interested of you to do that. And I will support you with data, but it's not the kind of things I like to do.
I'm glad you saw paper, because that's a wonderful archival paper. It isn't referenced very much at all.
No, for us was nice because, well, this is known. He think that from GM they had to do something like that, but without time frequency analysis, they just took this and say, let's measure the time here by hand. Was in the early 80s, and no one has done something like this. So I like this work because it's very, let's say, physical, old school thing, very step forward, and results are there.
Yeah.
Well, it's my opinion. I'm the father of this, so.
Yeah, they were trying to solve knock in airplane engines back, in the 30s.
So there's a new request for proposals should be coming out soon from ARPA-E. Chris Atkinson's an engines guy, but his program is going to be looking at connected vehicles.
How do you prefer?
Yeah, I didn't so my question, I think, is maybe you anticipate. So, is there we expected that program to be more engine related, but as it's evolved, it looks like it's going to be more powertrain. But I think the idea is, looking forward, looking ahead toward these connected vehicles and caravanning and things that might be ways to really reduce fuel consumption, increase efficiency. So can your work kind of move in that direction?
Because of the time, I skipped some slides. I was preparing for proposal, I can recover. I said that when you do things with the industry, you need to set your research, but it's the same with the public grants. So something we have, or I've been working in for some years now, and I think has some potential, is the RD framework. Well, it's not exactly the same, but it's just taking information technologies for making the engine to behave better. So this could be, let's say, optimal control for platooning and how to do that. But in our case, that was, let's say, engine related, that's not so important, it's only a part. But we thought about how to online optimize the calibration of the engine. So the thing is, at the end, you have a trade-offs, mostly consumption NOx.
Yeah.
So you can adapt this depending on the way.
That's right, so it's not only vehicle connectivity, but connectivity with cloud, so you can have computation.
The idea is,
on
if
cloud.
I have this situation, the city will say to me, yeah, I need you no NOx. So I prefer you to have lower NOx and you pay more fuel for that, and you can do that. And also, I can measure this and do that closed loop, and I could inform the town saying, well, today they say it's diesel burning, you cannot react the engine. My solution is different. I will say to you what's exactly the NOx quantity. And if I'm above a certain quantity, cut me or fine me. So this is the kind of things I think that could be really attractive for proposals. And let's say the open ideas is not only looking at the engine and just doing mechanical work or electrical engineering work, but thinking about, let's say, smart cities and mixed city vision. For sure, you can do also this with connected vehicles and just adapting your vehicle profile depending on the traffic and all that. And I was involved in some proposals in that in the UK projects.
You'll have just to respond to that. And you'll recall that
I was going to ask you,
we had a meeting with Chris Atkinson that you guys went to in Denver to support this RFP, and Guy Babbitt proposed a real-time marketplace for NOx that would implement exactly the same thing you're talking about, and it sort of generated general chuckles around the meeting, which I think means that that's exactly the right place to hit for RPE, right? We have to be on the border of laughably crazy, but probably doable.
And also this with lesser measurement, because the infrastructure could have that, but also as you have in the highways for measuring, you will have remote sensing of the NOx emission or the HC emission, doesn't matter. And you could, or we could in our cities to do something like that, let's say, to make the engine behave in a better way and optimizing the footprint, the emission footprint of the engine. So I get exactly the same response.
Yeah, right.
But when I was with someone from the European Commission, that is, let's say, the RIE equivalent, he was really interested into that. And also ICCT people, once with the pay for the Dieselgate discovery, they are also into these kind of things. So even if you don't do this, well, you could have a sensor and just send in the information of your emission and not waiting to, well, I don't know if you have here some technical inspection of vehicles, but I don't expect to be very restrictive as it is in Europe. That's not restrictive. So we could do that and ensure that the emission is in the level possible.
So what's, Brian said
Yes, I think someone was going to show me